Okay, so hopefully at this point in the lab, you have been able to take all of your data and you're starting to do some analysis. In the lab, it said that you should first draw a free body diagram of the system. I'm going to just draw one and we'll make sure that ours match. So here's my meter stick, and here is the balance point of the meter stick, or the center of gravity is what that's called. That's the middle of the meter stick. If there's nothing else involved in the system, that is where it will balance. But it's not what we're doing, because we're going to hang some masses over here. So here are my masses that I'm hanging, and in fact, once I do that, then my center of mass lives somewhere over here, depending on how much mass I have. Hopefully that's what you found. Now we want to make that into a free body diagram, so we need to draw some forces acting on that system. So hopefully when you were drawing forces, you had one going down like this. Maybe we'll call that the force of the earth on the stick. In parentheses, I'm going to write that as Fg sub s. And hopefully you also have a force over here, the force of the earth on the masses. So I'm going to call that Fg sub m. And there's one other force that's acting. It's not one that we really care about when we're trying to do the torque part, but there is a force that you're applying with your finger up like this. So this is the force of U on the stick, or you could say on the system, and we'll just call that an applied force. Okay, so hopefully your free body diagram looks something like that. As it says in the lab, we want to look at the net torque. The net force we know is 0. The net torque should also be 0. Let's take a look at how that works out. So the net torque is equal to the sum of all of the torques. Each of the forces is going to cause a torque, so I'm going to go ahead and label each of those. So I've got the torque from the masses, I've got the torque from U, and also the torque from the earth acting on the stick. I'm just going to call that torque sub S so that I'm staying consistent here with my letters. Now you can set this up really however you want. There's one very convenient way to set this up so that we can do analysis to find the mass of the stick, and that would be not worrying at all, at all about the force that you're applying. We can get rid of that in terms of torques if we put our axis of rotation right at the place where you're applying your force. That means that the torque, because it's force times the radius, the distance away, will go away. So that one's going to be a 0. When we look at the other two, we know that they are going to cancel each other out. One has to be positive, the other has to be negative. If we remember from our definitions earlier, we said that a counterclockwise force, or a counterclockwise torque, one that's going like that, we'll call positive. And if you look carefully at this one, the force of the earth on the mass will be the one that actually causes rotation in the counterclockwise direction. So we're going to call that a positive torque. Whereas the torque of the stick is going to be negative. It would make the system rotate in the clockwise direction if that was the only thing acting. As we said, we know that the torques have to add up to 0, so we now have got a net torque equation that we can use to solve for the mass. So this is where the algebra gets a little bit funny. It's not hard. I just wasn't confident that it would be something that would be really straightforward to try and write out. So that's why you're watching the video with me. It's nice to have you along. If we take a look at this, we've got one that's positive, one that's negative. They add up to 0, so I'm just going to put one on each side. So I'm going to say the torque of the mass has to equal the torque of the stick. We remember that torque is equal to the force times the radius. So that's going to be the force of gravity acting on the masses, or I'm going to break that down one more time and say the mass of the masses times the acceleration due to gravity times the distance. We'll call this distance here d, or maybe let's do r so that we're staying really consistent, r sub m for mass. And that is going to be equal to the mass of the stick times the acceleration due to gravity. Again, this is the force of gravity times the radius, or the distance over here between the balance point and the balance point of the stick itself. So I'm going to call that r sub s. Okay, so the whole game here, what we're really trying to do is to get an expression that we can graph so that we can find the mass of the stick. If we take a look at this, we can see that there's a g on both sides, so those are going to go away. So now we're left with m sub m times r sub m equals m sub s times r sub s. And then you're like, okay, well, I don't really know what's going on here, but there's one other little piece of information we know. We know where the balance point of the meter stick is all by itself. We know that the balance point of the meter stick is at 50 centimeters, or a little bit off from there. You can adjust this based on your findings. But I'm going to assume for now that the center of mass, or the balance point of the meter stick, is at 50. I can say that 50 centimeters is equal to Rm plus Rs. So what I'm saying here is that this balance point to here, which is 50 centimeters, is equal to Rm, the distance from the edge to the place where your finger was, plus the distance from where your finger was to the balance point of the meter stick itself. Using that, we can then substitute in and get what may look like an ugly equation, but it will really help us to figure out what's going on. So I am going to solve this, because I know that it will be helpful, for r sub s. R sub s will equal 50 minus r sub m. So all I did was to subtract the r sub m to the other side. And then I'm going to plug that r sub s in here. So now the expression I have is m sub m times r sub m equals m sub s times 50 minus r sub m. So if we look at this carefully, you're probably going, Ms. Carbling, what are you thinking? Why are you doing this? This is the thing that we're trying to find. We measured this, and we measured, excuse me, this. So now we've got things that we know, and we've got one thing we don't know. You may just want to solve that for m sub m, but that would be just plugging in one piece of data at a time. By graphing it, we can look overall at all of the points together. So we're going to do a little bit of algebra just to make this a nice thing, make it look something like y equals mx plus b, because as you know, that is the equation of a line. Yay, we love the line. So here we go. We are going to, I'm going to distribute my m sub s inside. So I've got m sub m, r sub m is equal to 50 m sub s minus r sub m, m sub s. A little ugly in the algebra, but trust me, it's going to be a good thing. I'm going to divide on both sides by r sub m. Remember, we measured that distance, r sub m. Okay, and cancel out here. Instead of writing this as one division, I can do it twice. So I'm going to divide by r sub m on both of these. My r sub m's are going to cancel, and I am left with an equation that is actually quite lovely. It says m sub m, so this is the mass that you were changing, right? You were putting different masses up there. That's the mass that you were changing, is equal to 50 m sub s, that's the mass of the stick, the thing that we're actually really looking for, times 1 over r sub m minus m sub s. Now you might say, Ms. Carbling, that doesn't look very pretty at all, but let me show you the beauty that it is. I'm going to take my y equals mx plus b, and I'm just going to throw it down here so that we can kind of look at them and we can compare. Take a look at what we've got now. This is pretty cool. M sub m is like my y. Okay, it's the thing that's all by itself. Negative m sub s is like my b. My y-intercept is not going to be 0. I measured r sub m. That's going to be my x value. And the slope of the line that I graph will be 50 times m sub s. So again, let me say that again. If I graph this, and on the y-axis I put m sub m, And on the x-axis, I put 1 over, and that's really important, the 1 over r sub m. According to this, we should get a straight line with a negative y-intercept. So the y-intercept will live down here somewhere. And a slope of 50 m sub s. I'm hoping that as you went through this, you followed along with the algebra. I do want you to go through and make sure you understand it. You are responsible for this, okay? So take a look through that. Once you understand that, talk to your partner, make sure everybody's happy. You're going to take your data and graph it, find the slope of your line, and use that to find the mass of the meter stick. Then go measure the mass of the meter stick, use a scale to find that, and then find a percent error. Hope that helps. Hope you guys have a great day. See you soon.